So I'm here with the 2023 Double Award Unit 6 Physics Higher paper. Just move over. There's your equation sheet. These we'll be using. Straight into question one. The first two really straightforward core knowledge, things that affect thinking distance and braking distance. Then this data is ripped straight from your theory test. So these measurements are standardized, so you'll see these all the time. You can see now 20 miles per hour, 6 meters thinking distance, 6 meters braking distance. And it's all about recognizing a trend now. You can see as you double the speed, the thinking distance also doubles, but then the braking distance quadruples by a factor of 4. And we're just going to talk about that then by year now. So we've got three statements. Thinking distance will half. The thinking distance will half from 12 to 6, but the braking distance will be a quarter. So decreases from 36 to 12 meters there for 3 marks. So we're disagreeing with some of these statements there for 3 marks. Down to the next question then, which is on half-life. So we're modeling half-life with the dice. So we need to know there's a random process. And we're going to agree because it smooths out fluctuations. And then this you'll see all the time. It reduces the effect of anomalies, or reduces the effect of anomalous results. It doesn't reduce the number of anomalies because it's a random process. You're going to get those anomalies, but having a large sample by adding 10 groups together will reduce the effect of those anomalies, so it won't impact it so much. For 2 marks per year then, we're saying that an eighth should decay. So the eighth has come from 1 in 8, so it's an 8, so 8-sided dice, so you've got a 1 in 8 chance of getting a particular number. So I'm going to convert that to just a normal number, but I can do that in the calculator. I can put 1 divided by 8 is going to give me this number. I'll times that by the number I start with. It gives me 63, which is approximately 60. Because if I take 60 from 500, I get 440. So a little bit of a numeracy question there. Then we've got a graph coming up. So you can see that I've made ticks against all of my plotting. So make sure, these are usually worth 3 marks. Yeah, 3 marks here. So we want a nice decay curve. One confident line. Can't have any wispy lines here. It starts at 500. It looks like the half-life is going to be asking me down here, which is 250. So I bring that across and then back down. And then I can see what my half-life is going to be. But let's have a look at the question anyway. There we are. So the number that throws is going to be 5.0. Now, you always go to the degree of accuracy on the graph, even though you can't really have... So let's just say this was 5.1. You can't really have 5.1 throws. It's either going to be 5 throws or 6 throws, but... because it's the degree of accuracy on the graph, always put that in. Now, they will accept just 5, but 5.0 is a better answer. But they will give you 2 marks for the line and then the answer. The experiment is repeated with 10-sided dice. Yeah, I suggest the data could be used to model decay with a shorter half-life. Do you agree? Well, fewer dice is going to decay because there's a lower chance of getting it. So you've got a 1 in 10 chance instead of a 1 in 8 chance now. So there's actually going to be a longer half-life. It's going to take longer to decay to get rid of those dice. So we're going to disagree there. Okay, next question is on Newton's laws. So Newton's third law, they're giving it you by here. So now you're going to have to kind of interpret if body A... So the body A could be the apple or body A could be the earth, and they're going to exert equal and opposite force on each other. They've given you some sort of force there, 1.5 newtons falling to the earth. Let's have a look at the questions. Is force Y is the gravitational? Yes. Force on the apple on the earth. So this is the earth, that is the apple. Okay. State how the forces X and Y, they're equal and opposite. It kind of says that in our question there. Right, but they're equal and opposite forces. And then we've got a little calculation. So use equation from page 2. It's going to be the weight calculation because we've got mass and we've got gravity. Gravity, the clue is there, G equals 10 newtons per kilogram or 10 meters per second squared because it's an acceleration. So I'm using my 1.5 from my mass, which I've highlighted up by here. It told me up there. and then I'm using gravity, which is 10. Okay, I'm literally just putting them in to the equation as I see them, and then I can rearrange or simplify, come out with 0.15 kilograms. State the initial acceleration of the apple. Well, the acceleration due to gravity is 10 meters per second, so it's going to be 10 meters per second. Next question then, at some time later, the air resistance acting on the apple is 0.25. So we've got air resistance, so it's still smaller, so it's going to still be speeding up until it reaches the terminal velocity. Determine the size of the resultant force. The resultant force is this arrow minus this arrow, and that's what we get, 1.25. The big mistake there is to use the equation that we're going to use now, because this F is the resultant force, is the leftover force, okay? This leftover force is equal to the mass of the apple and the acceleration, okay, of that apple. Well, in this case, we need to find the acceleration because we're asked to find the acceleration. But I know my extra force is 1.25. That equals my mass times then the acceleration. Quick rearrange, I can solve. My acceleration is 8.3 meters per second at this point, which is a little bit less because it will start decelerating. That doesn't mean that the apple is, because the apple is going to reach a terminal velocity. So I guess you could say the apple is not slowing down, it's just not accelerating as much, okay? Because that air resistance. Okay, this one divides the students because he predicted that if the hammer and the feather would drop together, they would drop at the same height and drop at the same time. So he's actually correct there, and there's a video to demonstrate this. It's because there's no air resistance, and because acceleration due to gravity is constant, this is going to be constant. No matter what mass you're dealing with, it's always going to fall at the same time. The acceleration is the same, so we're going to agree, because it's not affected by the mass of the object. Okay, so it's nothing to do with this equation here. Okay, this is something else completely. Lovely 6 marker by here then. It's a description of alpha, beta, and gamma, some properties, and how they can be safely stored. I'm not going to go through this because that's just going to waste everyone's time, but you can pause the video, but this really is core knowledge, and you should be getting really good marks from those 6. Maybe a tip is that examiners, especially physics examiners, they like it to be clear and concise, so I don't see any harm with bullet pointing, even though you're marked on the quality of your writing. It's a QER. The quality of the writing there is fine, and it's just split into segments that's easy to mark. You're demonstrating your knowledge and your writing ability there. You've got some nuclear equations now, a really generous 4 marks. I think this was 1 mark for this bit, 1 mark for this bit, 1 mark for this bit, 1 mark for this bit. So I'll just go through the top one. 231 plus 4 is going to give me 235. So everything on this side equals everything on this side. On the bottom now, 90 plus, we should know that our alpha particle has got 2 protons, 2 neutrons. So the mass number is going to be 4, and then the proton number is going to be 2. 231 plus 0 gives me 231, and then 91 plus minus 1 is 90. This is what catches students out. They always want to go 89 by here plus 1. But 89 plus minus 1 gives me 88. So be careful there for your 4th mark. Now, this would usually be a full colour diagram, but because this is a printout, it's in black and white. But the first question says, red giant star, 37 light years away from Earth. State how long that light takes to reach Earth. 37 years. Don't just put 37. Because it takes 37 years. Don't put light years either, because 37 light years is not a time, that's a distance. So you've got to be a little bit careful there with that 1 mark. Now, you could convert that in seconds, which we have to do down by year anyway. So I think they would accept that in there, because it says 1 year is 31,600,000 seconds, and the speed of light is this. So I'm going to take this formula because it's asking for a distance. We're given a time and we're given a speed. So it's just multiplying them together. And don't forget, it's 37 years. That gives us the seconds in 1 year, so I need to times that by the 37. Comes out with a gigantic number there, times 10 to the 17. Always write your answer as it says in the calculator. Okay, so whatever it says in the calculator, just put it in there. Okay, this is where the color diagram comes into effect, but we kind of know the colors anyway. Okay, so it says the sun and actors have different colors. Use the information there to compare the other properties. So actually, we're not comparing the colors because it's already told us that in the question anyway. So we can say that this star is bigger, it's brighter, it's cooler than our sun. How do we know that? Well, I'm just going to use the Hertzsprung-Russell diagram. Remember, the temperature is higher here and lower here. And then you've got that logarithmic scale there for luminosity. So we're just comparing our sun with this one. We can say there is actually more luminous, okay? It is actually cooler and it's bigger. It's much bigger than our sun. We can see that. Usually we can comment on colours as well. Then we've got a little bit on the life cycle of a star. And again, this is core knowledge. Should be knowing this. Hydrogen runs out, so helium fusion begins. And then in terms of forces, gas pressure is going to be bigger than the force inwards, which is gravitational, or gravity. 4 marks, nice, easy 4 marks. Okay, I think we're on to the last couple of questions. So this one is on energy and Hooke's law. So we're given a little bit there, and we're given a graph, force against extension. So let's have a look at the question. Use the graph and an equation from page 2. Now, this is the one that you've got to be careful of. You've got to go back and have a look because we're looking at work done. So I'm actually going to take the time and we're going to see what equations we've got for work done. Work done in stationary spring is the area under a force graph, and it's given us this. So a lot of people want to do this one because it's linked with spring. Some people, there's another one for work. I can't say, there we are, work force times distance there. Okay, but it's the area. So this probably is the biggest misconception because you've got a displacement and a force. So it'd be easy to pick this one. However, it's the area under a force force distance graph. So you can see how that extension, because measured in meters, a lot of people would use that distance because it's the same sort of thing. You'd still get marks for that. You'd still get a mark, okay? But you'd get double that. You'd get 1.8 then because you're not halving it. It would just be the fx. But we need to use that the area under the graph, which is linked up with that equation. Then it's going to give us an equation. It's telling us that our mass is this. We've already got our work done, so kinetic energy now is in joules, so we've got to make that link. Remember, energy can't be created or destroyed, it can only be transferred. So we already start with our energy, we've got a 0.5 from the half, we've got our mass, and then we've got a v squared. Now, they like these questions because you have to know now to square root the v to get v on its own, not v squared. Comes out to 4.9. What's the unit? It's speed, a velocity, so meters per second. 1 mark there. Explain why in practice the car will not reach its theoretical maximum velocity because energy is going to be lost. Okay, so this value here is never going to be as big as the theoretical value because you've got energy loss as heat, sound, friction, resistive forces, things like that. I think this is the last bit of the paper. So the car's maximum kinetic energy is found to be 0.8. Okay, so that's its actual, not in theory. Remember, it was 0.9. And a force brings it to rest at a distance 1.5 meters. So now we're going to use that equation. It's given us that equation there, okay, to do it. So my work involved is in joules, so 0.8 goes there. I don't know my force because it's asking me my force, but I do know my distance. Quick rearrange, divide both sides by 1.5, comes out to 0.5 newtons. And then the very last question, the spring constant for the spring used is 80 newtons per meter. Our MADI suggests it would be better to use a spring with a constant of 160, so double that because of the same extension, double the energy would be stored in the spring. Do you agree? Well, for the same extension, twice the force will be required, and if we use that half Fx and we double F, then the work will also double. So I'm going to agree with that, Okay, now that is quite a difficult question to end on because there's that link, but it is achievable, and I really hope you've got something from this paper. Thank you.